It's Thursday, my dude. It's Thursday. Now, what problem are we doing today? I can't see the screen, so I'm guessing 2487. That's what's on my mind. 2242, close enough. All right, so today we're doing problem 2242. There's 3 2s. 3 plus 1 is 4. 4, 2, 2, 2, 2, 6, 6, 4, 10. Numerology. Okay, so let's go ahead and get right into this problem. So, we're trying to find the maximum score of a node sequence. What could it mean? So there's an undirected graph with n nodes numbered from 0 to n minus 1. We've seen this before. You're given a zero-indexed array, integer array, scores of length n, where scores I denotes the score of node I. You're also given a 2D integer array edges, where edges of i's ai, bi denotes that there's an undirected edge connecting nodes ai, bi. All right. It's unweighted, but there's a graph, and each node has a certain weight associated with it. A node sequence is valid if it meets the following conditions. There's an edge connecting every adjacent node in the sequence. All right, so it's like a path, right? A path has to go through edges. You can't just transport from one vertice to another vertice if there's no direct edge or there's no undirected edge between them. And no node appears more than once in a sequence. All right, so this valid path can't traverse the same node twice. Maybe if there's a cycle, you could start at A, then go to B, then go to C, then go back to A, then go to D, like this, right? So that's not a valid path because you crossed this point twice if these were 4 nodes. All right, so a valid path has to go through sequential nodes, and there has to be edges in between each node. Okay, the score of a node sequence is defined as the sum of the scores of the nodes in the sequence. Return the maximum score of a valid node sequence with a length of 4. If no such sequence exists, return -1. LaGuardia Leviosa! Okay. So, let's draw out this example. So we got this node. Trying to cover my big forehead. 0, 1, 2, 4, 3 over here. Then we got these connections. Kind of looks like a kite, right? One missing piece. All right, and then these are nodes 0, 1, 2, 3, and 4. And the scores are a 5, a 2, a 9, an 8, a 4. So the output is 24. What was the length of this? Maximum score of a sequence of length 4. So we need a path with 4 nodes in it, where there's no repeat nodes and there's edges between each node. So the figure above shows that the graph in the chosen node sequence is 0, 1, 2, 3. Okay, so there's just path 0 to 1, 1 to 2, 2 to 3. All right, and then that has 7 plus 8, 15 plus 9, 24. So if you add up these values here, you'll see that your path length is 24. Now, I don't think that's the only way to get 24, because you could also, what else could you do here? Pretty sure you can use one of these. Yeah, like this path is also valid. Right, and it's also 24. Yeah, 3, 1, 2, 0 right here. It's also a valid path. Ah, where did it go? Okay. And then in this example, there's nothing, right? Because there's no way you could get, right? You can't repeat nodes. You can't go like 0, 3, 3, 1, 1, 3, 3, 5, right? It has to be a path with all unique edges that you traverse, right? Length of 4. All right, so how do you do this problem? Well, I know a trick, and I saw this while I was studying at Berkeley. And it was a similar problem. since we're looking at a path, right? No matter how the path looks, right? If it's like in this system, right? Like the path looks like this. I'm saying like it goes like that, right? You can always stretch out a path for any system. It's going to look like this, right? There's 4 nodes and there's a path connecting them. Now there could be additional connections from each of these things, right? These things could also connect to each other, so I don't really know what this system looks like. So I'm going to draw this huge cloud here around it. What I'm basically saying is like there could potentially be, there could be a connection here. Oh no, there already is a connection there. There could be a connection here between these 2 nodes, right? This system could connect here. Right, there's all sorts of additional connections that we don't know about. But if you just zero in, like if I zero in on this system here, right, regardless of what it looks like in here, there's definitely this path. Where these things have 5, 2, 9, 8, right? And there's this other system on the inside, but I'm just saying you can look at any path as, that has this shape and this relationship. Okay. So what does that mean? Well, I'm going to ignore for a moment the additional edges and just zero in on a path. Well, for a max path, right, we could look at an edge, like this edge here, and we'll call this W, U, V, and X, right? The maximum path for U and V, so we look at each edge, right? Because there's always going to be this center edge in a path. That's what I'm trying to get at here, right? There's always a center edge in a path, right? So we look at this system that I've just completely destroyed with markings, right? There's a path associated with this edge, right? And it's here and here, right? There's a path associated with this edge, which is, it could be this and this, or it could be this and that, right? But what we want to find is the max path for an edge, right? Because for every edge, if it has at least one neighbor, one unique neighbor, right, there's a path between these nodes. Right, there's a path. So how do we find the maximum? Well, you can have multiple edges, right? And X can have multiple edges. So these W's are like candidates. Oh, I'm an idiot. That's why I was like, that looks confusing. So this is X2. X1, X3. Okay. The maximum path is going to be UV for this edge, and then it's going to choose one of these and one of these. And whichever one is the maximum, like imagine W3 was the largest on this side, we choose that, and we choose that. Trying to think about how to describe this. So if we want to find the max path for every that includes an edge, we look at the max neighbor of one side of that edge connection and the max neighbor of one side of the other connection. So the max path for an edge UV is the score of U, right? The score of this system plus the score of V, right, that's here, plus the max score of W for the neighbor W we'll say in neighbors of you plus the max score of x for x in neighbor of v. So I'm basically saying here is the score for this edge, the path including this edge, is the score of u plus the score of v plus the max of this and the max of this, right? Because again, when you have the system, when you're looking at this system here for u and v, the path already includes this edge, so whoever is the maximum neighbor will create the maximum path, right? And maybe it's that. I don't know. I'm just kind of choosing one arbitrarily to prove a point, but that's the idea here. So you have scores of u, scores of v, max scores of w and neighbor of u, so that's going to pick the maximum of this. Max scores x and neighbors of u, and that's going to pick the max of this. So that's the general idea. So what we want to do is we want to look at each edge and do this relationship to find each path, including that edge, and then return the maximum. But before we do that, there's a small constraint that we need to consider. Right? There's a few edge cases which are going to make this kind of difficult. First thing we have to make sure we do is, first constraint is, when we look at the neighbors, it's kind of like an observation of u, we don't want to consider v, right? Because I said that here, we're going to look at the max scores of w for w's and neighbors of u. Well, these are w values, right? But v is also a neighbor, right? When I say neighbors of u, when this is constructed, right, like this is a neighbor of u, this is a neighbor of u, this is a neighbor of u, and v is a neighbor of u. So it's possible that your largest neighbor is v, but you can't have a path. Your path has to include one of these values, right? It can't include v, right? Because the path can't use the same vertice twice. So it can't include this v value. And it's possible, like for, let's just say for an example, counter example to what we did before, these have 1, 2, 3, 4, right, 3. When u picks its maximum neighbor, it's going to be inclined to pick v, but it can't pick v. So we need to ensure that when we choose a neighbor, we don't choose v. Okay. What else do we have to consider? Well, a second observation is, right, when we look at this system here, we just assume that u's neighbors aren't v's neighbors, right? But let's work on another counter example using this same system. What if, instead of like this, because this system can have cycles, what if instead formed like a triangle, and this was w3 as well as x3, and say this had value 10, 1, 1, 1, 1. So when u and v choose their maximum neighbor, right, what are the neighbors of u? What are the neighbors of v? Well, we've already trained the system now. We've added this constraint. We've considered the fact, okay, don't have u look at v and don't have v look at u. So we don't need to worry about this. These neighbors here, right? We've kind of resolved that issue. But when u looks at its max neighbor, it's going to be like, okay, 1, 1, and 10. All right, I choose this one. Right? And we'll do that in blue to specify the path that it chose. And when v looks at its neighbor, say 1, 1, and 10. Oh, I choose this one. So then the final path is this triangle, which is obviously not a valid path form. So when we look at neighbors, so the next constraint then is, well, if U and V share a neighbor, then what? We can only select that neighbor once. Okay? So to do this problem, what we could do simply, now I'm not going to write the code for this, is you could build a graph and you could look at each edge, UV, and then look at each neighbor of U and each neighbor of V, and then run through a maximum, making sure you're meeting these constraints. Okay? So there's E edges, and each vertice could have at most E neighbors. So that's E squared runtime. So that's too slow. Okay, so the thing is here is what we should do while we're building this graph is consider how many neighbors do we need to maintain inside of our graph to ensure that we find all maximums, so that we don't want to consider all of our neighbors, because that's going to take this system here, this is going to take E squared time, right? So how many neighbors do we need to consider to find a max path for any edge? Okay. Well, if you look at a node, two nodes like this, right? And I'm considering what neighbors of U do I need to look at? Well, I definitely want max neighbors, right? So I'm going to say, well, give me the max neighbor of U. Okay, so I need at least one neighbor of U to consider to find this max path that includes UV. Okay? But it's possible that that neighbor is also a neighbor of V. So we can't just consider one max neighbor to find this max path. Okay, so now I need to consider another one. All right, well, I'll take the second maximum neighbor. All right. Well, it's possible that this maximum neighbor is V itself, right? It's possible that I choose my second maximum neighbor, but it's actually V. All right, so I need another one. So then I grab my third max neighbor. Right, so I only need to check my 3 largest max neighbors to make sure that these conditions are met. Because if one of them meets this condition, it can't be met again, right? I only have one neighbor that's V. And if one of them meets this condition as well, then it can't happen again. So then the third maximum is the best one to try. So I only needed to get the 3 maximum neighbors for U and V to find the max path. So I can do this system again, but instead of looking at each neighbor, look at 3 maximum neighbors. And this runtime, instead of being E squared, is now E. And then we'll have to look at each pair of neighbors. So it's 3 times 3, 9. 9E, whatever. It's just going to be big O of E operations to do this. So just by looking at the 3 maximum neighbors, because 3 maximum neighbors, at least one of them will not succumb, I guess, to one of these constraints. So if I just look at the 3 maximum neighbors, then I can do it in linear time. So we're going to go ahead and do that code here. So the first thing we're going to do is we're going to create a graph. For graph, what am I doing? Graph equals this for blank in range length of scores, right? Because scores is the number of nodes. And then what we'll do is we'll say for UV in edges. But we're trying to keep the 3 largest neighbors for each node, right? And largest means the highest score. So we're going to say if G of U if the length of G of U is less than 3, because we only want to keep the 3 largest neighbors, we're going to say heap Q, that heap push, we're going to push into G of U the scores of U. Wait, we're trying to push the neighbor, so V is the neighbor with that score and that value. Else, this means that there's already 3 elements, so we need to remove one. So we'll do, I think it's called heap push. I need to look that up. Sorry, heap push pop. Yeah, heap push pop. Okay. And then we'll do the same thing for V, because we're just trying to get the largest neighbors for each node. So length of V. We're going to push into V, U, score U. We'll push into V, score U, U, and we'll move the minimum. Okay. So now we have the system of the 3 largest neighbors. And then we're going to look at each edge again. We'll have a max score. If there's no max score, we return -1. So we'll say max score equals -1. We'll look at each UV and edges. And then we'll look at each neighbor W in the graph of U. And we'll look at each neighbor V in the graph of V, W, neighbor X in the graph of V, right? And then we're just going to make sure the constraints are met. So what's the first constraint? Well, if W equals V, or X equals U, so W can't equal V, and X can't equal U, and X can't equal W. Right, so when we look at the system again, right, W not equaling to V, right, because I'm looking at the neighbors. Let's get this situated here, looking a little nicer. It's a beautiful thing. W not equaling to V, right? Well, that's saying like this is a neighbor W, so it can't equal V, right? And X can't equal U. Well, when you're looking at X's neighbor, right? X's neighbor, it can't equal U. And then saying X can't equal W, well, if you have these 2 neighbors here, right? This is where W and X are equal. That can't happen either. So you're just looking at all those 2 constraints we had and writing them into the system. Right. Now this is score of W. Right, because we pushed it like that. Score of X. So if this is the case, then we can see if this is the new max score. So max score equals the max, or whatever our current max score is, right? Because we're looking at each edge. So additional edge might have a valid path, but it might not be a good solution. And then we'll say, well, there's scores of U plus scores of V plus score of W plus score of X. And then we'll return max score when we're done. And we'll submit that and pray. See, I did this earlier today and I did it wrong. All right, there you go. So that's the answer. So what's the runtime of this? Well, we got to look at each edge. There's E edges. So that's big O of E. What am I doing? So that's big O of E edges, right? People say, well, you're doing a heap operation. right? But I'm always constraining that the heap is less than 3. So that's 3 log 3 or whatever, right? Operations that we have to do in the heap, but since the heap is constrained to being only size 3, it doesn't grow with anything, so it's constant. So these are constant operations in here. So this stays at O of E. Now here you say, okay, there's a for loop and a for loop and a for loop. Obviously this outer for loop goes through each edge. So that's big O of E, right, where E is the number of edges. Schnauzer! But this for loop, well, G of U, right, is this heap which only has 3 elements. So this has 3 elements, right, and this has 3 elements. So this is only going to take 9 operations. Again, that's constant. It doesn't grow with anything. So that's also constant operation. So this is O of E. So it's O of E time plus O of E time, 2 O of E, which is O of E runtime. Okay, what about space complexity? Well, if V is the number of vertices, so the number of scores, right, we need to create a system for each of those. So we have V vertices. So that's O of V space. And O of V. Yeah. And then here, you know, we grow each of these kind of lists, these heaps inside of G, but since we only constrain to size 3, it's the same story, right? We don't ever have more than 3 elements in each vertex, so it's constant. So it's O of V space. Same here. We're not creating any additional variables here. So I mean, we are, but nothing that grows with either scores or edges or anything like that. So O of V space, where we call this scores. All right, and then O of V edges, you call this length of edges runtime. All right, everybody. I hope that made a little bit of sense. This is one of those problems where you got to think about it. And if you don't get the intuition, you're probably not going to get the answer. And that doesn't mean you're dumb. It just means that this problem is hard. See ya.